In mathematics, we describe waves by partial differential equations, and there are dozens and dozens of wave equations out there, and I'm not going to list them all, but I just want to show you what two of them look like, at least to a mathematician. So some of the two most basic equations, wave equations that we study, one is called the wave equation, or the free wave equation, and it is what, for example, sound waves or water waves to a first approximation. And so there's a scalar field, U. So it might, if it's a water wave, it might just denote the amplitude of water on a two-dimensional surface. If it's a sound wave in 3 dimensions, then it would be working in 3 dimensions. And it's a double time derivative of U equals Laplacian of U. And then another important basic equation is the Schrödinger equation, which describes quantum waves of wave functions of one particle. And it's very similar, except that now the wave function is complex valued rather than real. And you stick an I in here, and there's only one time derivative instead of 2. But basically, a very similar equation, at least algebraically. If you work in the sciences, maybe you don't write the equations this way. You might see a few more C's and H bars and 2 M's and so forth. So mathematicians, by convention, we often normalize all those interesting physical constants to 1, so you don't see them. And of course, in the real world, the world is 3-dimensional, but we often, in mathematics, we like varying the dimension, not just for sake of generality, but often just to vary the difficulty. So a lot of these problems are in a certain dimension, like 3 dimensions might be too difficult or too easy to study. And so it's a convenient parameter to modify to get to a question where somehow you can make interesting progress. In mathematics, you always want to work on questions that are just barely outside of the range of sort of known techniques, because then you have a chance of making progress and advancing the field. If it's too easy, if you don't learn anything, and if it's too hard, you also don't learn anything. Now, these are the two simplest models. As I said, there are dozens and dozens of other equations that are more physically realistic, but generally speaking, you have no hope of understanding the difficult models unless you first understand the simple models, like the free wave equation, free Schrödinger equation. And even for these most basic models, there are still questions. I mean, we're making a lot of progress, but actually there's still questions we don't fully answer. We don't fully know the answer to, even for these basic models. But they're often the first step. You can use things like perturbation theory often to understand, say, nonlinear versions of these equations once you understand the linear version. Okay. So there's lots and lots of topics in the mathematical theory of waves, and there's no way I can summarize everything that's going on. And there are already several talks in this series actually covering various aspects of wave equations. But one theme, I think, which is common, at least in the mathematical study of waves, is that waves, as opposed to other equations like the heat equations or transport equations or whatever, they exhibit two phenomena which kind of fight each other. And this sort of tension between these two phenomena I find fascinating, about waves in particular. So the first is energy conservation, that waves, at least ideal waves where there's no friction, they conserve energy. So energy is neither created nor destroyed in a system modeled by a wave equation. And it's not just energy, there's a couple of other energy type quantities that are also preserved. So that's one feature of wave equations. The technical, the more technical term is that these are Hamiltonian equations. But then the other thing which is kind of fighting this conservation of energy is that they also like to decay. That waves tend to diminish as time advances. And these two facts are kind of contradictory. How can something be both conserved and decaying? And quantifying exactly how these two phenomena sort of interplay with each other, that's really, I find that kind of a common theme in the subject. Although formalizing exactly what that means, you kind of lose this intuition and you just see lots and lots of math. But this, I think, is some of the basic fundamental feature of waves. Okay, so let's talk about energy conservation first. There's a nice quote by Isaac Asimov, which I quite like. Yeah, the law of conservation of energy tells us you can't get something for nothing, but we refuse to believe it. it is a very unintuitive law, actually. I mean, I think it took a while after Newton, actually, to figure out even that energy was a thing and that it was conserved. It's like energy is unlike, say, mass or something, it's not something that you can really kind of measure and touch directly. But it is an important law that physical systems have. And so, as I said, these idealized wave equations, like the free Schrodinger equation, they have no friction, no dissipation, no interaction with external forces or other particles. So, as we learn in our physics classes, whenever you have a closed system without these dissipative forces, we expect energy to be conserved. So mathematically, what that means is that there'll be some quantity called, so at any time, so your solution, your wave is called u, and at every time t, there is, your wave has a certain profile, u of t, and so u of 0 is the initial state of the wave, and u of t is the state at some later time. And at every state of the wave gets assigned some number called the energy. There's an energy that you can assign to the wave at any given time, and the law of conservation of energy says that the energy at time t is always equal to the energy at time 0. And so, I mean, the powerful thing is that this is true for all time t, so it doesn't matter what kind of interactions go on. You can have extremely complicated dynamics, but no matter what you do, you must always keep this energy conserved. It's not always energy. As I said, there are also conservation of mass sometimes, or in the case of the Schrodinger equation, conservation of probability. Yeah, so the energy for waves tends to take various integrated forms. When you strip out all the physical constants, for example, the energy of a free wave takes a form like this. It's the integral of the surface energy, which is basically the square integral of the gradient of u. Measures this. It comes from surface tension of the wave, and then there's also the kinetic energy, half mv squared. But because we've normalized m to be 1, you just see the 1/2 and then the time derivative of u, which is the velocity of the wave. Okay, so that is what energy looks like for the wave equation, and there's a similar formula for the energy of a free Schrodinger particle. It's just down there, and again, the h bars and m's and so forth have been suppressed. But also the total, by Born's law, the square of the wave function is the probability density, and the probability that your particle is somewhere is always 1. Okay, so the total probability is also conserved. Okay, so these are what conserved quantities look like. So why do we have conserved quantities at all? I mean, this is it's not intuitive, and people spend lots of time trying to build perpetual motion machines and things trying to defeat the law of conservation of energy, because it isn't really an intuitive law. I mean, people are either naturally kind of optimists, they think that things get better over time, or pessimists, they think things get worse over time. But I think that the idea that things are conserved over time is not really intuitive. But it is a general phenomenon that pretty much any physical system actually has lots of conservation laws, and so it comes from a really fundamental theorem of. So this was explained by Emmy Noether. So Emmy Noether has her famous Noether's theorem, which says that every time you have a physical system and it has some sort of symmetry attached to it, more precisely a continuous symmetry, then your equation must come with a conservation law. And in fact, there's kind of a converse to it. Every conservation law comes with a symmetry. So there's this fundamental and not intuitive connection between conservation and symmetry. Yeah, so first of all, this is asterisk about physical system. Okay, so not every, if you have an arbitrary equation, usually nothing's conserved. But it's only the physical equations that get conservation laws. And physical has a technical meaning. It means that either you obey classical mechanics, Newton's laws, Hamilton mechanics, and Lagrangian mechanics, or you obey quantum mechanics, Schrodinger's laws and Heisenberg's law. For both of those, we have Noether's theorem. Okay, but for anything else, you don't, pretty much. But then once you have Noether's theorem, you've got this great dictionary. Every time your system has some symmetry, it creates a conserved quantity. So here's some examples. So if your system, for example, is what's called spatially translation invariant, which means that if you take your solution to a wave equation and you just move it in space somewhere else, it still solves the same equation. If your equation doesn't privilege one location in space over another, it has spatial translation invariance. And Noether's theorem tells you that every time that happens, you have a conservation of momentum. If you have rotation symmetry, you conserve angular momentum. If you have what's called phase rotation symmetry, you conserve total probability. You have gauge transforms, you conserve charge. If you're invariant, if your equations are time translation invariant, they don't privilege time zero over any other time, then that's where energy conservation comes from. And then there's a really fancy symmetry that sort of contains all the previous ones to some extent. The principle of general relativity says that the laws of physics should look the same in every single reference frame, even the non-inertial ones. And that leads to actually a pointwise conservation of stress energy, which is sort of, in some sense, stronger than most of the previous ones. But we won't talk about that one. Okay. Yeah, so I want to give one proof in this talk, and it's a proof of Noether's theorem. I don't know how well known it is. It's a proof, I learned it from this lecture of Richard Feynman, who gives famously good lectures, or used to give famously good lectures. And so, and it's a proof, I mean, it's almost a proof by picture. I mean, you have to accept a few things on faith. Okay, so in case you haven't seen it, I just want to show you why symmetry and conservation are so tightly interwound. Okay, so all physical systems, Hamiltonian, like from classical mechanics or quantum mechanics, they are all what's called Lagrangian. They obey a variational principle, sometimes known as the principle of least action. So for every one of these equations, there is some complicated quantity called the action, and it's some big space-time integral of your wave. And solutions to wave equations are always trying to minimize this action. Actually, technically, they are stationary points from the action, which are slightly different than being minima, but you can think of it as being minimizes. Maybe the version of this that you may have seen, maybe even in high school, is Fermat's principle of least time, which he used to try to explain the behavior of optics. That if you look at the behavior of light, think of it as a particle, photon, from trying to get from A to B, photons will always try to take the path that minimizes the time to get from A to B. And this is why, for example, when there's a mirror, angle of incidence is angle of reflection, because that is actually mathematically, that's the path that will minimize the time, at least locally. Of course, globally, you could go straight, but locally, that's the minimizer. Also, it explains Snell's law of refraction. If you pass from air to glass, you bend, and the bend is exactly what's needed to minimize the time of transit. All right, so that is one very famous example of a variational principle. Okay, and it turns out that all waves, of course, we now know that light is an electromagnetic wave, but in fact, all waves obey a principle of least action. It's just different wave equations have different actions. And I'm not actually going to write down any of these actions. I mean, you can, but it won't really illuminate anything. It's actually not important to the proof. All right. So mathematically, what does being stationary for the action mean? So you can think of a way, mathematically, so the great thing about mathematics is that you can, well, first of all, you can draw diagrams and they can mean whatever you want. The x-axis here is what's called state space. These are all the possible states of waves at a given time. And this is an infinite dimensional space because waves have infinite many degrees of freedom. So this line here is actually denoting an infinite dimensional space, but to a mathematician, that's completely fine. So at any given time, your wave is just one point in this state space. And then what a wave is some trajectory over time. Yeah, so the vertical axis is time. So at some initial time, you're at some initial state, and then your wave does something, and then you end up at some final time. So you can think of a wave as some curve in an infinite dimensional space. And what being stationary means is minimizing the action. The action is normally called L for Lagrangian. Is that if you take your actual trajectory, so this is the actual path of your solution, and then you take any competing trajectory. So if you take some other possible behavioral wave that doesn't solve your equation, but it has the same initial and it starts at the same state and ends at the final state, but it does something close to, but not exactly the same. The principle of these actions is that your actual solution U is a stationary point of the Lagrangian, which means that any nearby perturbation has almost the same Lagrangian as your original Lagrangian to first order. To second order, there'll be a little bit of a correction, but as a first approximation, changing the trajectory of your solution doesn't actually change your path much. That's like if you go in a straight line from A to B, any slight perturbation of a straight line takes almost the same distance. Okay, because of Pythagorean theorem.